Welcome to the Bodhi Academy. My name is Amisha Klaso, and in today's video we will continue with the last part of our chapter Solutions, class 12, chapter 1. So today we will talk about one of the colligative properties, that is the depression in the freezing point. So depression in the freezing point, when we say, we talk about a temperature when the solid and the liquid forms a substance of the substance are in equilibrium with each other. That is, the solid and the liquid form of the substance have the same vapor pressure and they coexist with each other. So when we are talking about the depression in freezing point, we are saying that the solid which is present, okay, and the liquid that is formed in the liquid form of the substance, these two together, they have the same vapor pressure, okay, and they can coexist together, as in they can exist with in each other's presence. So it is a characteristic of each liquid. So one example of this is the freezing point of H2O is known to be 273.15 Kelvin. Now it is observed that the vapor pressure of the solution is lower than that of the pure solvent. This we already know, that the vapor pressure of the solution is lower than that of the pure solvent that is present. Thus, a solution has to be cooled further to get the freezing point of the solution. So now if we want to obtain the freezing point of the solution, what we have to do? We have to lower the solution even lower, because the vapor pressure of the solution is already lower than the pure solvent. So the decrease in the freezing point of the solution due to the addition of the non-volatile solute to solvent is called depression in the freezing point, and that is denoted by Tf. So now let T naught F be the freezing point of the pure solvent. So pure solvent freezing point is T naught F, and Tf is the freezing point of the non-volatile solute that is present in it. So the decreasing in the freezing point, that is delta Tf, will be given by T naught F minus Tf, where T naught F is the freezing point of the solvent and Tf is the freezing point of the non-volatile solute that is present. So this is the depression. This equation gives us the depression in the freezing point. Now when we talk about dilute solution, we know that Raoult's law is applicable. So which says that delta Tf will be directly proportional to m, where m is the molarity of the solution. So on removing the proportionality sign, we get delta Tf equals to Kf into m. So we add a proportionality constant, that is Kf. Now this Kf which is given here, it depends on two things. One is the nature of the solvent, that is known as the freezing point depression, or it is also known as the molar depression constant or gyroscopic constant. So now if we substitute this molality given as a W2 upon M2, so we can substitute this molality as W2 upon M2, that is given weight upon the molar mass of one upon the given weight of the other into 1000. So this, now if I substitute in this above equation, instead of m I substitute the molality formula, I get Kf into, this will be W2 upon M2 upon W1 into 1000. So delta Tf will be equal to what? Kf into, on rearranging this equation, will get W2 into 1000, this is 1000, upon M2 into W1. So now if we have to find a molar mass of any one of them, we can find it by using Kf into W2. Kf is the proportionality constant, W2 into 1000 upon, this is a depression freezing point, into the weight of the given solute or solvent. Now let's talk about another property. The last property is the osmosis and osmotic pressure. Now we already know, we know simple examples of osmosis. When we say we take mango and we put it in some saline water or oil solution, what happens? It starts to shrink up, okay. Same thing happens if we disperse our blood cells, red blood cells, into saline water, they also tend to shrinken up. So this is an example of osmosis, where there is some movement of solutions that is happening. So the movement of solvent molecules from a less concentrated concentrated solution to a more concentrated solution through semi-permeable membrane is termed as osmosis. Now in this example that we discussed previously, the basic thing that is happening is that the molecules are traveling from one place to another. They are more specifically, they are traveling from a place where there is lower concentration to a place where there is a higher concentration, correct? Now what is happening here is that if this movement is happening, we can say that there is some kind of membrane that is present, because if there was no membrane, no such movement would have occurred. So there was no place for those molecules to actually travel. So this membrane is known as the semi-permeable membrane, okay, and this is responsible for osmosis. So the movement of solvent molecules that happens from a less concentrated solution to a more highly concentrated solution through the semi-permeable membrane is known as the process of osmosis. Now hydrostatic pressure which develops on account of osmosis is called as the osmotic pressure, or the excess pressure that must be applied on the solution to prevent osmosis is called as the osmotic pressure. Now this, if I had to write it in terms of expression, I'll write it as pi equals to CRT, where C is the concentration, R is the gas constant, and pi is the osmotic pressure, and T is the temperature. Now if I know, I can write this concentration as N2, that is number of moles of solute, upon V, that is the volume of solution in liters. So this C, if I substitute here in this, I get pi equals to N2 upon V dot RT dot R dot T. So pi can be also written as, now this N upon 2, this N2 that is moles of solution can be also written as the weight, that is the given mass upon the molar mass. So if I substitute, I'll get W2 upon M2 the whole divided by V dot RT. So now from this, if I want to find the molar mass of any one substance, I can find it as W2 upon V pi dot RT by rearranging the same equation. Now let's look at some of the interesting terms that we have. So two solutions having the same osmotic pressure at a given temperature. So any solutions which have this their osmotic pressure, that is pi, is equal at any given temperature, then such solutions are called as isotonic solutions. So if one solution is of lower osmotic pressure, it is called hypotonic with respect to more concentrated solution. So the more concentrated solution is said to be hypertonic with respect to the dilute solution. So here this is a bit confusing. So just remember, if we have a solution which has a lower concentration of it has a lower osmotic pressure, then it is called as hypotonic with respect to the higher concentration solution. If the solution is more concentrated solution, then it is called as hypotonic with respect to the dilute solution. Now if a pressure higher than the osmotic pressure is applied on the solution, the solvent will flow from the solution into the pure solvent through the semi-permeable membrane, and this process is called as the reverse osmosis. Now what they are saying is that if we apply a pressure, okay, a external pressure that is already higher than the osmotic pressure that is present in the solution, in that case what will happen, the solvent will flow in the reverse direction, that is it will go from the solution into the pure solvent through the same semi-permeable membrane. So when this process of osmosis is reversing, it is known as the reverse osmosis, and this is used in the desalination of sea water. Now let's talk about abnormal molecular masses. So when the molecular mass of a substance determined by any of the colligative properties comes out to be different than the expected value, the substance is said to show abnormal molecular masses. So now we have spoken about all the colligative properties, we have spoken about 4 of them. So now what does this abnormal molecular mass says that when in all of them, what we have learned eventually at the end, we have done to find the molecular mass, that is M2 calculation we have done, okay. So through that we can get the estimated value. But now if the value, okay, by calculation whatever we are getting is different from what is actually supposed to happen, that if there is a difference in both the, say, the observed value and the calculated value, the experimentally the value that we are getting is, say, different than the one that we have actually calculated, in that case we can say that the substance is showing a abnormal molecular mass. So abnormal molecular masses are observed when a solution is non-ideal, that is not dilute, or solute when a solute undergoes association or dissociation. So only in two cases abnormal molecular masses are seen. First is when the solution is non-ideal, that is not, it is highly concentrated, and second is that it undergoes either association or it undergoes dissociation. Next we have the Van Hoff factor. So if it is defined as the ratio of the experimental value of the colligative properties to the calculated value of the colligative properties. So applying Van Hoff factor, we can say we can associate it as a ratio of the experimental value of the colligative property to the calculated value of the same. So if we are having I equals to, in that case we can say the normal molar mass that we are actually supposed to get and the abnormal molar mass. So the ratio of this. So this, if I now write it in terms of colligative properties, I can write it as observed value of the colligative property upon the calculated value of the colligative property. So I will be here equal to total number of molecules of particles that are present after dissociation / association, either of them, upon the number of moles of particles that are present before association / dissociation. Now how do we know if there is association happening or dissociation happening? Now say if the value of I is less than I, we can say that the solute particles are undergoing dissociation. If the value of I is greater than 1, we can say that the solute particles are undergoing association in the solution. Now, inclusive of the Van Hoff factor modifies the equation for colligative properties as follows. So, for substances undergoing association or dissociation in the solution, the various expressions for colligative properties are modified as follows. So, all the colligative properties applying this Van Hoff factor and the abnormal molar mass thing, we can modify all the properties that we have done. So if we have here first one, for relative lowering of vapor pressure of any solvent, we can say that P naught I equals to P naught 1 minus P1 will be equal to P naught 1 equals to I dot N2 upon N1. Then for elevation of boiling point, we can say that delta TB equals to I Kb M. M is the molality. Depression, and this Kb here is the proportionality constant. Depression of freezing point, we will have delta Tf will be equal to I. Everywhere we are adding the abnormal molar mass factor, that is the I. Kf, again the proportionality constant, and M is the molality. Osmotic pressure of a solution, again P will be equal to I N2 RT upon V. So like this, in this way, applying the Van Hoff factor, we can modify the equations of the colligative properties. Okay, so that was it for this chapter. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy. Thank you.